I've watched Landscape Live talks for years. I'm excited to actually be sharing some work with you. Um, so I'm going to be talking about non-local transport and kind of a new way of looking at hill slope modeling. Before we kind of get to non-local stuff, let's kind of think a little bit about why do we care about hill slopes at all, for those of us who maybe don't think that much outside of rivers or our other geomorphic regimes. Let's see. There we go. Right, so hill slopes, they are a very large percent of the landscape that most of us live on. The processes that happen on hill slopes control sediment delivery to rivers and a lot of things downstream. There are long-term land use and climate change impacts and geologic hazards that happen on hill slopes. So, we need to think about these things both in terms of our longer scale geomorphic landscape kinds of problems and more applied shorter term human problems. So how do we model hill slopes? The earliest model that's still used by a lot of folks today is very simple, based on the observation that hill slopes tend to be convex, where we essentially relate the sediment flux on a hill slope to a linear function of surface slope. We call this term D of diffusivity. So it's just an empirical scaling relation. This is considered a diffusive flux law because when we assume that the soil flux is proportional to surface slope, we end up with a steady state mass balance where so erosion rate is equal to tectonic uplift steady state. Leads us to a parabolic equation for hill slope profiles, which is a nice kind of elegant solution. Real hill slopes, however, can really only get so steep before they start to collapse. So beyond a certain slope, they stop being parabolic and develop planar side slopes at some maximum stable slope. So we tend to see hill slopes, especially in active tectonic areas, with parabolic tops and then planar side slopes representing the kind of frictional limit for soil stability at some critical gradient, SC. So a more realistic approach to modeling this kind of landscape is a nonlinear flux law, which will invoke an infinite flux or asymptotic behavior, like this, in sediment flux as a function of surface gradient, so that as slopes approach a critical value, the fluxes approach infinite rates. So this kind of approach is really useful for modeling long-term mean erosion and steady state morphology. We can calibrate our this term transport efficiency, which is similar to the diffusivity in the previous equation, using long-term erosion rates. And it does a decent job for these kind of steady state long-term problems. The challenge, though, is that this is also an entirely phenomenological model, so it really lacks any connection to the mechanics of transport, which means that it's agnostic to process. So if we zoom in to look at actual steepland fluxes, as in this data from Roaring's 1999 paper, it turns out that different processes and their distinct mechanics are responsible for a lot of variability, especially in steep landscapes. One process that's very common in steep landscapes is dry ravel, or the rolling, bouncing, sliding of sediment downhill rather than soil creep. So, for example, I think it's a disturbance-driven. You can see just from these two videos how there's quite a lot of variability in the flux triggered by any given dry ravel event that produces this sort of very noisy real data with respect to surface gradient. Oops. Oh, there they are again. So if we think more generally about steepland fluxes through a mechanistic lens, we might realize, especially those of us who think about hill slopes, what's really happening under the hood here in terms of this kind of very noisy data is a combination of increasing soil cover, heterogeneity or patchiness, and decreasing soil stability, which means that mobilization rates are becoming dominated by large stochastic disturbances like landslides, bioturbation. And then once sediment is mobile in steep landscapes, it also travels much longer distances downhill, which means it's encountering uneven topography and vegetation, maybe patchy bedrock exposure. And that all leads particles to develop kind of a path-dependent memory, or what we call non-local transport, where particles are seeing parts of the landscape upslope. So what we're really getting at with these two different effects here is it's a matter of entrainment and disentrainment, which are two kind of fundamental descriptions of particle motion that we don't think about when we use the diffusive flux laws. So to dig into that, entrainment is really, it's a measure of how often and how much material starts moving. Disentrainment is a measure of how far it goes before it stops moving. And breaking fluxes down into these terms is useful so that we can consider them independently as variables, both in time and space, which is especially important in steeplands where terrain is heterogeneous and transport is driven by these patchy and stochastic disturbances like burrowing animals. And these things can entrain and disentrain material at different rates along the hill slope. So for example, higher rates of burrowing in one location might entrain more material down here. Can you see my mouse? Yeah, good. Down here than upslope. And then we might also see varying disentrainment downslope, even at points with equal surface gradients, say down here and over here, if the ground upslope of one point is steeper and particles gain more momentum. Or for example, if there are different amounts of vegetation or other obstacles to particle motion in the way that can influence particle paths. So a fundamental limitation of the diffusive flux models is that a diffusive flux law is also a local model, meaning that it estimates flux at a position X based only on the characteristics like slope at that position X. And a local flux model, regardless of its form, will never be able to capture these spatially variable entrainment and disentrainment conditions. It'll always predict identical fluxes at any points that have identical conditions. So for example, here I'm showing these points x1 and x2, which have equal slope and very different conditions upslope of them. But if conditions are the same at each of these two different points, a local model like Josh's nonlinear flux law will always predict the same flux at these points, regardless of what's happening upslope. So a better way to account for this kind of motion is through convolutional models that integrate upslope fluxes and conditions by convolving an entrainment rate at each position. Here I'm calling position X prime is the point where stuff gets entrained. Entrainment is formally defined as the probability of particles starting to move at any given position X prime. And we convolve that with an exceedance probability, or the likelihood that a particle that is in motion will travel past a given position downhill. It's essentially a travel distance distribution. So if you aren't familiar with convolutions, we're just looking at kind of the amount of material that starts at any position X prime along the hill slope, say where a squirrel is burrowing, and then we're multiplying by the fraction of material that will still be moving by the time it reaches us somewhere downhill at position X. And then by integrating, we're just summing over all of the possible X prime positions or squirrels along the hill slope. So ultimately, this is giving us the sum of all the sediment that's originating from upslope of a given position, X, and traveling at least far enough to pass that position. So In this talk, I'm going to be focusing on kind of a very probabilistic particle transport focused applications of this model. But I want to hammer the point that this is really a flexible model framework that in this form is really agnostic to process. But unlike diffusive frameworks, it's providing us with an explicit link to entrainment and disentrainment, which we can then use to examine any number of processes across a wide range of scales and levels of granularity. So you'll notice there's no physics in here yet, but because these are physically meaningful terms, we could replace them with functions representing any process we want. So related approaches have been used in rivers and depositional systems in the geosciences, and in physics and astrophysics, they've been used to model the movement of atoms and galaxies. This is a model that Einstein actually used in 1905. So the other thing I want to highlight here is that historically, we've often used entirely different approaches to address local transport, which is well captured by diffusive models, and non-local transport, which is fundamentally not. So this travel distance exceedance term, though, gives us an avenue to incorporate both of them in this same model. So so ultimately, the form of the distribution, the travel distance or exceedance distribution, is what distinguishes local from non-local transport. Exponential distributions and distributions with tails that are lighter than exponential means that the collective behavior of particles can be described by variability around a mean field or central tendency. So for example, here's an ensemble of quails moving as a mean field, and their collective movement is really well described by the mean invariance of all of the chicks, because none of them are going too far afield. But if enough particles travel far enough, specifically enough of the distribution of their travel distances becomes heavy-tailed, then their collective behavior can no longer be described by a mean field. So formally, that's because when the mean of a distribution gets heavy enough or contains enough extreme values, the mean or the variance becomes undefined or approaches infinity. So the travel distance exceedance that we use here and that I'll be showing you a bunch of data for today, this is really just another form of a travel distance probability distribution. It's actually 1 minus the cumulative distribution or the complementary cumulative distribution. And one very practical aspect of the exceedance form of a travel distance distribution is that it makes it really easy to distinguish the distribution form. So a light-tailed distribution in exceedance space is concave down, whereas a heavy-tailed distribution is concave up. Here, an exponential is linear, but a concave up heavy-tailed distribution means that unlike a light-tailed distribution, there's no point where the probability of exceeding some maximum value goes to 0. And that's why heavy-tailed distributions like power laws are often used as the identifying mark of non-local transport. So historically, people have applied local flux laws to cases where we can assume short light-tailed travel distances, and then have used a suite of other non-local models to describe fluxes with longer travel distances that we can assume have heavy tails. So my colleagues and I prefer using a Lomax distribution to model travel distances. A Lomax distribution, or also called a Pareto type 2 for those of you who care, it's a convenient form of distribution for modeling travel distances because it can describe both light-tailed and heavy-tailed distributions, or local and non-local transport. So we have light tails or local transport are represented by distributions with a shape parameter, this a value that's less than 0, and then an exponential distribution at a = 0, which is the dividing line between a light and heavy tail distribution. And then we transitioned into heavy tail distributions for positive A values. So that A value gives us a kind of an easy way of distinguishing whether any fluxes we're looking at are going to be heavy-tailed or light-tailed or non-local versus local. And then B is a scale parameter, which describes how far particles go overall, which we'll look at more later on. So an important point here, though, is kind of bringing this back to physical things, is that the travel distance distributions are fundamentally controlled by the physics of particle disentrainment. And we can solve for disentrainment both empirically and from the distribution form to explore what's physically responsible for each of these distribution forms. I know we don't all spend our time thinking about the statistics of particle motion, but we would love to link it to actual physical conditions in the world that we can then use to get to a more physically based model of fluxes. So if we look at kind of a theoretical cartoon, the disentrainment probability or the probability that a particle in motion will disentrain or stop at some given distance, the physics here really comes down to a balance between kinetic gains by conversion of gravitational potential as particles are moving downhill versus loss of kinetic energy to friction or inelastic impacts. So here we're looking at a light-tailed distribution, and this is associated with what we call bounded particle motion, meaning that particles are increasingly likely to disentrain the farther they travel, which represents the outcome of net kinetic losses. So friction and inelastic collisions are winning here. For example, from some rock drop experiments, there is some maximum distance that bounds particle travel distances. So fluxes will be very short in this kind of condition. Okay. Exponential distributions are produced by uniform disentrainment rate, meaning that particles are equally likely to disentrain at any given position, which is also a random or Poisson process. And that really reflects an average balance in kinetic energy as particles travel downhill. So gaining an equivalent amount of kinetic energy as we're losing to friction. And then heavy tail distributions or non-local transport occurs when particles run away or become less and less likely to disentrain the farther they go because of net kinetic gains over friction. So you notice that in these videos, I'm showing the rock size is increasing, which makes sense. If any of you have ever, trundled rocks down a hill, the bigger ones obviously tend to go farther. And this is the fundamental advantage of this type of model. It's probabilistic, so we're not necessarily, counting for every single particle, but it has clear links to physical controls. So for example, we also know intuitively that particles will travel farther on steeper slopes. So we're more likely to shift our distribution toward a heavy tail in that way. And going back to the role of vegetation, which I'll focus on a lot in this talk, it turns out that surface roughness also plays a really significant role here. So this is from some rock drop experiments I did with Josh Roaring and others at 2 field sites in the Oregon Coast Range a few years ago, which have the same surface gradient, and we're using the same collection of rocks in these experiments. And there's a 1.5 centimeter difference in the median roughness of the surface here because one of them was burned recently. So just a very small surface roughness difference. And okay. And in these histograms of particle travel distances, you can see that although about 20% of particles traveled more than 4 meters on this smooth burned slope, some of them quite a bit more, up to and past 30 meters. None of them made it past 4 meters on this only slightly more rough vegetated slope. If we transform our travel distance data to look at the disentrainment rates and exceedance distributions, we can see that that tiny 1.5 centimeter difference in micro roughness is associated with a really significant difference in transport from runaway motion and associated with heavy-tailed or non-local travel distance exceedances appear on these smoother burn slopes, and bounded motion or non-local light-tailed local light-tailed motion on the rougher vegetated slope. So this convolutional framework kind of unlocks our ability to get at hill slope process mechanics because two major advantages relative to diffusive models. First, we can explicitly address these independent changes in entrainment and disentrainment processes, which are often governed by distinct mechanics and processes. And then by using a probabilistic approach to the travel distance term, we can consider both local and non-local transport, as well as the physical controls that dictate the particle behaviors. So for the rest of this talk, I'm going to show you two short case studies where we actually use this framework to work toward new perspectives on hill slope problems. So first, we'll look at biotically driven dry ravel after wildfires to see how changes in probabilistic descriptions of particle motion might give us new insights that can inform future predictions of post-fire processes and hazards. And then we'll go to some coarse periglacial deposits following the last glacial maximum, where we'll look at some approaches to forward modeling the full convolutional flux to investigate potential changes in soil production and transport as climate warmed after glaciation. So both of these are ongoing projects, so I'm not going to completely answer either of these questions today, but I hope to convince you by the end of this talk that the model framework I've just shown you has the capacity to help us unwrap these and other complex hill slope problems to get at the mechanics in a way that's both tractable and critical, really, if we're going to answer some of our most pressing questions around climate change and landscape evolution in geomorphology today. So let's jump in. So in our first case study, and we're going to do a deep dive into the effects of roughness and particle size on on dry ravel after wildfire, which I know not all of us are in the arid west of the US, but here and in many other places in the world, climate change is shifting our wildfire regimes very significantly to more frequent, more intense fires. And so trying to understand the landscape response, including short-term responses here, is becoming increasingly important. So returning to the idea of vegetation as surface roughness, the reason that this is an important problem here is that in vegetated regions, plants often form what some will call a sediment dam or capacitor, or vegetation traps sediment wedges on their upslope side. And then when that vegetation burns away during a wildfire, not only do we reduce the surface roughness, as I already mentioned, but we also are releasing that trapped sediment to travel far downhill as dry ravel. Oops. So this is potentially a very large amount of sediment. Dry ravel is the primary form of post-fire erosion in most steeplands. It can increase post-fire erosion rates up to 30 times relative to long-term rates, and it accounts for up to 75% of total long-term sediment budgets in some places. So this is really important if we want to be able to predict long-term responses in steepland fluxes or erosion rates as wildfire regimes shift. And recent work has also shown that dry ravel deposits in channels can fuel post-fire debris flows. So if we want to better predict debris flow initiation or runout, we need to know what's loading the channel, and our current models can't predict that. So we need better connections here between dry ravel transport modeling and site-dependent parameters that are controlling where, when, and how much dry ravel is going to get dumped down these hill slopes. So we have studied these connections at the Blue Oak Ranch Reserve, which is one of the University of California's natural reserves in coastal California. This area burned in the Santa Clara Unit Lightning Complex fire in August of 2020. It's located here just east of San Jose, south of the San Francisco Bay, in the Diablo Range. And so throughout this landscape, sediment transport here is occurring really primarily by soil creep during the rainy season, which is wintertime and relatively short and late. But in the summer and immediately following the fire, we see large amounts of dry gravel that are driven by bioturbation, mostly by burrowing rodents like this guy, the California ground squirrel, and Boda's pocket gopher and others. So this is near one of the classic landscapes where many people have characterized kind of biotic, bioturbation-driven, and especially gopher-driven transport. So this entire region of California is very squirrel and gopher controlled. They're digging up here a mix of coarse gravels and especially on our study hill slope, some really cohesive soil aggregates you can see here in coming out of this squirrel burrow just after the fire. So the fire has given us an opportunity to examine particle motion through this non-local framework. The gravels and soil aggregates that the squirrels are excavating traveled downhill en masse after the fire. You can see them here on the hill slope and in the channel here. So a mix of gravels, but also quite a lot of these they're really just these balls of very hard dirt that you can crush if you try. And just for scale, this is a little box here is 10 centimeters. So this is an example of a very large one that's rolled down. So the low burn severity at our site incinerated the grasses here, but it didn't disaggregate. It wasn't hot enough to disaggregate all of these soils. So we've really just reduced the surface roughness. So we visited the site 6 months or so, every 6 months or so, for about 1.5 years after the fire. And over that time, the site experienced quite a lot of pretty rapid recovery. So this is in September of 2020, about a month after the fire, March 2021, 7 months after the fire, July of 2021, a year later, and March of 2022, about 1.5 years after the fire. So we can see the vegetation growing back, and then at some point, we're starting to see surface roughness that's probably governed by the annual grass growth cycle rather than more post-fire recovery. So we have collected a range of data I'll show you across several cross-slope transects on the south-facing slope of a small catchment. This is about a 1 square kilometer catchment. We're looking at a steady transect along this south-facing slope. And that slope goes through a range of surface gradients and steepens toward the channel. So we can see the effects of slope changes on particle transport here. So, all right. So in this photo I showed you, we were conducting Woolman-style pebble counts across the hill slope to measure grain sizes. We did this in 10-meter intervals down the hill slope, or cross-slope transects every 10 meters down the hill slope. And then we also collected individual soil aggregates to do short-lived exposure dating, which I'll discuss more later. So the grain size distributions that we measured should be interpreted with a few things in mind. So first, there was a sudden leaf drop right after the fire in October to November of 2020, which actually provided a really convenient leaf layer in the channel at the toe of the hill slope, which bounds the post-fire channel deposits. So that means that when we measured grain sizes in July of 2021, our measurements really represent the deposits from about 2 months to a year after the fire. when we look at the particle sizes for this period, we see that the channel deposits are significantly more coarse than the toe slope here across the entire distribution. You can also see the median 50th percentile and 90th percentile grain sizes for each of our cross slope transects by distance from the ridge line here for our 3 different study collection times. So on that visit in July 2021, we actually excavated all of the material above the leaf layer to isolate future deposits. So the measurements from March 2022 then represent new deposition from about 1 to 1.5 years after the fire. And over that period, we see channel and toe deposits fining. So July to March next year. Same thing here. Since vegetation is recovering during that period, we're assuming that the first post-fire measurements represent post-fire deposition of coarsened material relative to the pre-fire state. So we're assuming we're looking at post-fire recovery back toward a pre-fire state. So previous studies have observed a range of post-fire responses from post-fire coarsening, like we're seeing here, to post-fire fining. So for example, here's data from a recent study by Al Neely, where it was in the San Gabriel Mountains of California. So and here they saw a fining of channel deposits at sites with significant dry rubble fluxes. And we could chalk this up to, just different sites are different, which I think is often, what we think about when sites are very variable. It's hard to get at the details, right? But we'd really like to be able to dig into understanding what makes different sites different or behave differently, because that variability matters, right? Whether gravel deposits coarsen or fine, channel deposits, it makes a difference to debris flow hazards. The ratio of fines to coarse material is relevant to initiation and to debris flow rheology. So we'd like to be able to dig in. So to that end, let's look at the non-local transport. So in addition to measuring grain sizes, we also did a bunch of repeat rock drop experiments here, 3 cross slope transects using 3 different particle size classes of the soil aggregates that we found on the hill slopes to paint them so that we could find them once we dropped them. And like the rock drop experiments I showed you previously, here are the results from March 2021, looking at our 3 different cross slope transects from near the ridge line, lowest slope, to steepest at the toe down here. And then each column is one of our grain sizes, going from about 0.5 centimeter, 1.3 centimeters to nearly 3 centimeters into intermediate diameter. So just from this first data set, we can already see that 7 months after the fire, there's very clear heavy-tailed transport happening for the large and medium particles on the mid to toe slopes, meaning that these particles are traveling far enough downslope that we could not capture them with a diffusive flux model. By July, all of the steepest slope and largest particles, everything except for the steepest slope and largest particles here, has transitioned to lighter tails. So gone more towards straight or concave down travel distances. But even a full 1.5 years after the fire, at this steepest site for the largest particles on the slope, we're still seeing heavy-tailed travel distance distributions, suggesting that at this site, a diffusive model is going to completely miss the influence of the largest particles, how they move on the slope. So even among the sites that, and the smaller particle sizes that aren't noticeably heavy-tailed, we can also see the influence of vegetation regrowth in shifting our distributions toward lighter and lighter tails. All that really seems to matter a lot less for the smallest particles, which are kind of bouncing all over the place. So if we put these things together, we can kind of tentatively infer a storyline here. The largest particles seem to have been evacuated or fully entrained from the hill slope into the channel immediately after the fire. Large particles are then resupplied over time by burrowing. But non-local transport is continuing to move the large particles farther down slope, maybe over coarsening the toe bit. And as vegetation recovers and non-local transport declines, the coarse particles are repopulating deposits eventually. Another interesting point here, though, is an undergrad student in my lab, Sam Burton, has separated some of these individual soil aggregate particles into radial layers. She's using a little nutmeg grinder to analyze their lead-210 concentrations. Lead-210 is a short-lived radionuclide delivered by rainfall with a half-life of around 53 years. So it tells us about decadal surface exposure. And we find that most of these aggregates have a radial decay in concentrations, which means that they're staying coherent over decadal timescales rather than rehomogenizing with the soil nitrics, say, every year. Although we can see at least some evidence of mixing with these particles. So here the largest points are the outer shell of the particles down to the smaller shell. So more higher concentration to lower concentrations is a depth profile. And here some of our layers are swapped, meaning that these particles must have at some point broken apart and remixed. In addition, Raul Kaushal is a postdoc in my group, and he's been conducting some wetting and drying experiments. His results suggest that although these particles don't disaggregate with partial or even full saturation, they do fall apart under full submersion or oversaturation conditions. So observationally and from overland flow sensors around the site, we think overland flow is extremely rare at this site. We've yet to see any. So this is consistent with Sam's finding, and it suggests that for the most part, these aggregates are acting like coarse particles when they're being transported, but they turn into fines once they're in the channel and it floods. And that has important implications for post-fire hazard modeling, because the relative fractions, again, of fine and coarse material play an important role in reflow initiation. So this helps us fill in kind of this parameter space around how sediment moves after fires, where it's going to end up, and what are the implications. And this question of coarsely transported material that then turns into fines is an interesting one that I'll leave exploring that to future work. And wrap this up with a few takeaways here. Surface roughness and grain size are these key controls on steepland transport. The larger particles travel much farther on smooth, steep terrain, which has implications maybe for kind of time or disturbance-dependent critical slopes, if you want to think about it that way. For example, compared to the study I showed by Al-Neely. The larger transport of non-local transport of larger grains caused measurable downslope coarsening after fire until the vegetation regrew. So that suggests low attainment or shorter travel distances for the smaller grains might explain the discrepancy with the thin soils and bedrock slopes. Again, from other studies like Al's, where downslope fining has been observed. So we really should look more into the entrainment. And then another point here is that seasonal or post-disturbance variation in the vegetation and surface elasticity, soil cohesion, bioturbation, all of these things, these might play important roles in moderating the role of non-local transport in steeplands. And those are things that we can also address through different terms in a convolutional model. So I'm not going to go there in this study, but is an interesting avenue for future work. So I will go quickly through this one. In our second case study, we'll look backwards instead of forwards, and we'll actually get to looking at the convolution model. So here we're looking at some post-LGM periglacial deposits and thinking about what could we infer about soil production and transport processes from these rapidly deposited deposits. So this study is a collaboration in the Whitewater Valley of Minnesota with several colleagues from the upper Midwest of the US. It's based on work by Joe Mason and Jim Knox at the University of Wisconsin, Madison. So during his thesis in the 1990s, Joe Mason mapped a number of coarse periglacial deposits from after the LGM in the upper Midwest. If you've spent more time than I have learning about geomorphology in like Minnesota and Wisconsin, you might be familiar with these. They're relatively well discussed. So we're going to hypothesize here that these deposits formed largely as a result of two things. First, cryoweathering and cryoturbation processes that are active in cold climates are known to both drive rapid weathering and denudation in alpine environments and to coarsen the mobile material that's being produced in alpine environments. And then second, we already know that in the absence of large vegetation, that coarse material would travel long distances. And from data dating the deposits and from beryllium-10 erosion rates, we know that these deposits came down up to around 14,000 years ago, post-LGM, and beryllium-10 suggests that erosion rates during this period were 1.5 times modern rates, particularly in this study area. This is a figure from Shanti Penfrey's, a PhD student working with Andy Wickert, where she's been looking at, who also did the beryllium-10 dates, and she has been looking at pollen record literature. So we know that the climate warmed after the LGM, so the cryoweathering processes we hypothesized shut off, and then by around 14,000 years ago, trees started to show up in the pollen record. Now, at that point, trees would stabilize slopes, increasing the soil residence times, causing mobile material to fine as gluvium weathers in place, and then the large vegetation showing up would also reduce travel distances for the material once it's entrained. So I'm not going to get all the way to testing this hypothesis in this talk, but we'll use Joe's data to show you how a non-local convolution can let us explicitly model each of these processes independently in a way that's not feasible with diffusive models. Oops. Okay, so we're using data from a site that Joe mapped in Whitewater Valley in southeastern Minnesota. This is a coarse deposit around 1 meter thick from carbon-14 dates. We know it was deposited over about 1,000-year time span. And it's preserved on a terrace. So from its dimensions, we can get a rough lower limit on a total deposit volume over 1,000 years. And we know about 65% of that volume is composed of coarse material, which here is sourced from a dolomite capstone layer at the top of the hill. So this is a spatially constrained source area with material that's being detached and entrained from the top of the slope and then traveling down to the bottom of the slope. And again, so in the previous study, we really only were looking at the travel distance exceedances. Here, all of these data provide useful constraints on erosion deposition that we can use to look at the full flux convolution with both entrainment and disentrainment. So we can estimate an entrainment rate from the total volume of dolomite in the deposit divided by the dolomite source area and the time span of deposition. And then unlike in the last study looking at specific physical controls on the travel distance exceedance, here we'll look more theoretically at the parameter space for travel distance exceedances to see how sensitive the outcomes of this model are to varying the form of that distribution. So in other words, I'm just going to model the flux for a range of A and B values, losing our Lomax distribution again. Okay, so before I look at model results, I just want to quickly show you what the travel distance distributions look like across a range of values to get a better sense of kind of what we're doing. So I'm going to show you a bunch of model results. It's a lot of them, so don't get overwhelmed. We're looking at a range of A values, which again are showing light to heavy-tailed transport, with the sea green color being an exponential distribution, which is cut off between the brown light-tailed or local values and the blue heavy-tailed or non-local travel distance distribution. let's see, the scale parameter B, which I said I would mention later, is it's really just I'm showing 3 different values here, 1 to 50 meters. And obviously, if we have a larger B value, for example, this is showing distributions traveling or particle travel distributions traveling much longer distances. The dashed lines here are mean values for those distributions, the light-tailed ones that have a defined mean. An important point I just want to show you here is that the B parameter here is, we call it a scale parameter because it's really just scaling the travel distance distributions. So for example, if we look at our exceedances scaled to an appropriate distance for each of these distributions, we can see that the scale parameter is really, well, we can see that, I guess, the non-local transport here is it's a scale-independent process. You can have heavy-tailed distributions or non-local transport over very long and very short time scales, which is an important point that I think we often miss when we think about non-local transport as just a long-distance problem. So theoretically, it can happen at very short distances is the point, I guess. Okay, so let's actually look at models. So this is an analytical solution to the non-local flux equation. So I'm just plugging in a Lomax distribution and integrating over the hill slope. The dashed lines here show the end of the dolomite bedrock exposure or the entrainment source area. This zone at the end is where the 1 meter thick deposit should start. So I'm just manually redistributing any material that travels past this point. And we are not re-entraining anything here. So we're saying everything moves once at this entrainment rate we estimated, and then it sits there. So under this model, and I should point out, this is the model flux versus position, and this is the net deposition over 1,000 years. So under this model, 2 main things to point out here. The first, the light-tailed fluxes, the brown tones here, with a limited source area for the entrainment, the flux is dying out rapidly outside of the entrainment zone up here, since the material is disentrained and then no new material is entrained. And as a result of that, the light-tailed fluxes really can't move material very far down the hill slope, even with really long 50-meter mean travel distances. So the exponential distribution here, this guy, is really barely just starting to deposit material at the terrace. The only way to build a substantial deposit at the toe is through non-local transport. But again, this approach doesn't include any re-entrainment. So, so we can make some really different decisions about how to treat re-entrainment. This is the last thing I'll show you. It turns out how you treat re-entrainment behavior makes a real big difference in flux scenarios. So a few models just to demonstrate. So these are all iterative time step models with assuming 1 transport event per year. So this is an example of we might call a detachment limited model where so the bedrock is entraining at that rate that we estimated, and then the entire deposit just re-entrains in every event. So anything that's not attached immediately just rolls down the surface. And so we can see under this scenario, this is for a local light-tailed distribution. We build out a distribution from the top of the hill slope, downslope, and then it's going to look a little funny as we build up our deposit at the toe. So we eventually build a deposit out. I'll let that keep going for time's sake. Oops. We can also look at kind of a conditionally detachment limited scenario where bedrock entrains at the same rate, and then the deposit re-entrains only at that same rate until it's exhausted at any given position. And for that one, because we're not re-entraining everything, we, again, really don't move stuff too far down the hill slope. We're providing a constant source of material at the at this dolomite source area, and it's never really making it too far down the hill slope, but a little bit of it, a thin layer, if you were to zoom in on this model, a thin layer is building up. And in some of these, at some point, we start to build a thin layer of deposition at the toe. And then finally, if we start bringing in like a weathering limited condition where the bedrock is not entraining unless it's exposed, then I'm not going to show you a video for this one because it's a little boring. But we have a hard time building up material downslope unless we have either heavy tail travel distances or a very, very long mean travel distance. So again, these are just theoretical kind of toy models, but it demonstrates that the reentrainment behavior really makes a big difference on how the deposit ends up looking. So the deposition depends both on the travel distance distribution and on the reentrainment behavior. Some takeaways here are that this convolution is allowing really flexible incorporation of variable sediment sources, one which we can't do through a nonlinear local model. And those spatial patterns in the deposition could end up providing clues for inferring details of entrainment or disentrainment. The time step also matters. I didn't really show that, but how frequently you start stuff moving makes a difference. If we're, releasing stuff small volumes more frequently or one large volume very infrequently. And then it's unclear at this point whether non-local transport may have contributed to these post-LGM deposits, but it's possible, I'll say. More work is needed there. Okay, so I will maybe leave some last conclusions up here so we can get to questions. But one point I do just want to raise here is that, again, while I showed all of these models kind of on this very particle probabilistic focused techniques, this really is a very flexible and process agnostic model. So those terms for entrainment or disentrainment or travel distances, we could use a probabilistic term, as I've done here. You could also put in physics and use a mechanistic term or phenomenological terms. So it can be adopted to different transport processes and scopes. And you could also include multiple process components or a time or spatial dimensions to expand this model over like across additional convolutional terms. So very flexible. I think more people should start thinking about hill slopes from this kind of shifted perspective of what are the kind of tractable ways we can get at these underlying pieces of sediment transport in a way that's allowing us to treat different processes in explicit terms. And I will stop there because I'm quite over time. Apologies.
Thank you so much, Danica. It was really, really interesting. So the chat is now open, so please go ahead and share with us your questions. We still don't have any, so can I make you just a very simple question? I got really interested in the relationship that you were trying to find with the post-fire research and studies that you have been developing. I was wondering if you ever look or think of looking at to the effects of long-lasting drastic temperatures on soil aggregation, on a surface roughness, if that makes any sense or not.
Did you say long-lasting changes in temperatures or drastic temperatures?
Drastic temperatures, yeah, drastic changes.
Do you mean in terms of climate shift or in terms of like fire burning soils?
In terms of climate.
Yeah, I think that if you kind of look at the intersection of these studies, we have not looked at this explicitly, I guess, but I think that it's the kind of problem that you could look at either empirically. For example, if you were to incorporate different terms, phenomenological terms, say, for how you expect different temperatures to affect either entrainment or disentrainment. Or if you have a physical model for that, you could incorporate these terms. I'm not sure if that gets entirely at your question.
Thank you. Okay, and there's a question in the chat from Luca. He says, thank you, Danica. When you consider the further distance of travel on a burn slope, it is also accompanied with a greater probability of knocking further grains off their spot and triggering cascading motion of multiple grains. Associated questions, are multiple grains moving together able to travel further than a single grain?
That is a really good question. And yes, so the experiments that we've done are Dave Furbish would call it rarefied particle motion, where particles are dispersed enough that they are not interacting with one another, which I think is kind of a simplification, because at some point on this gradient of particle interactions, you start running into granular flows, which are governed by pretty different physics. That grain-on-grain interactions are really dominant there. But I think in our experiments, we absolutely see that, one, particles do knock stuff loose, which is, maybe we could account for this through a probabilistic entrainment term, and maybe tie together our disentrainment and entrainment terms. But also, as you build up deposition, then you start to, that feeds back on the disentrainment, where, for example, in our experiments, if you build up enough rocks on the ground, they start to pose an obstacle to other rocks rolling down the hill, as you can imagine. So I think that this has, I guess I will just say that because this model is process agnostic, it does have the capacity to deal with a granular flow. You would just need to adjust, what you're putting in as entrainment and disentrainment. Those terms are, there's nothing particle-based that's fundamentally explicit in those terms. And then I see Matthew Morris has a question. I understand non-local transport much better now. No, oh, it's just a compliment. Thank you.
I guess I have a very quick question maybe before we finish. I am conscious of time. It's a similar question actually to what Rita asked, but it sort of relates then to kind of how much have you sort of factored in the substrate or the characteristics of the hill slope that you're doing. I'm sorry, I'm talking about the fire example. Yeah. And just in change, I mean, I know that Rita talked about temperature, but just in terms of moisture, if you have daily or seasonal variations, then, for example, in kind of the moisture content of your hill slope or the soil that's on the surface, how might that affect some of your simulations?
I'm so glad you asked. Let's see. So I did not show this data in this talk, but we actually have looked at this a bit. So I only showed you data from the south-facing slope here, but this is a paired north and south-facing hill slope. There's a paired north and south-facing hill slope in this catchment, and the north-facing slope is actually very different. So there's an aspect-dependent moisture difference here, which is really common in particularly arid climates, Colorado and California and other places of the world, where the north-facing slope, due to solar aspect, retains more moisture, and therefore there's a difference in vegetation. So there's a lot of oak trees on the north-facing slope. There's also a lot more mosses, and it's a lot less dominated by the seasonal grass regrowth. And then during the spring, we see a lot more kind of squishy surfaces on the north-facing slope. There's also a structural control on the north-facing slope, so it's a lot more rocky. So first off, this is just the kind of best fit lines to the travel distance distributions on the south and north-facing slope, including one site on the south-facing slope that I didn't show. But and then here the darker colors here are spring of 2021, going to lighter colors later in time to spring 2022. And one thing we notice when we look at these is that we don't see the same clear shift from heavy tails to light tails over time on the north facing slope. Essentially at all. There's a couple places where maybe it shows up, but it's unclear enough. And you know, it's going the opposite direction, for example, here where we're seeing a light-tailed distribution in spring of 2020 and going to a heavy-tailed distribution the next year. So at this site, we suspect that the seasonal variation in vegetation is really what's controlling travel distances. We also think that in the spring versus the summer, even on the south facing slope, the surface is more squishy. We tried to characterize this using a Schmidt hammer, and it turns out a Schmidt hammer is really not the right tool it thinks all those soils, even when they feel rock hard, are just squishy. So we have plans at some point to go back and better characterize elasticity seasonally. But one important point here is that here I've collapsed all of the travel distance data from the north and south facing slope across all time periods onto a modified exceedance probability and dimensionless travel distance, which is essentially if they're fitting a Lomax distribution correctly, then it would fall on this one-to-one line. So we can at least see that regardless of the gradients, roughness, elasticity, soil moisture, etc., the Lomax model is doing a good job of capturing the distributions of data on these slopes. But I do think there's some very interesting variability in how these hill slopes are responding to fire, essentially.
Cool. Thank you very much. Thank you.
Oh, hi, Samantha.
Okay, so we don't have questions, but we have a compliment from Samantha Motz that she really enjoyed your talk. Anyone wants to put last questions? No?
I guess I'll just throw in a question. It's not really my field, but I wonder if there's any influence of the severity of the burn of the wildfires on your experiments, and if either, you know, there's some variation in terms of recurrence interval or how hot like a specific burn gets on because that might generate, I guess, some variations in the hydrophobic layers of these soils. And so is there anything that you're doing pertaining to those nuances of the fire regime?
Yeah, so that's a great question. At this particular site, the way that we have, well, both the way that we're approaching the study and the nature of the fire at this site, because it's a low burn severity, there really is no hydrophobicity on the south facing slope. I actually first went to this site because Margaret Zimmer was studying aspect dependent hydrology, and her study site burned down on her. So we started out looking at soil permeability and post-fire infiltration. And there's some patchy hydrophobicity around trees that burned on the north-facing slope. But the south-facing slope, really just the grass burned down in a quick flash. So for our purposes, it's a convenient kind of field experiment where we've lowered roughness without inducing hydrophobicity. But you're right, if we want to think about the longer term influence of changing wildfire regimes, a higher or moderate to high burn severity fire will potentially induce hydrophobicity, which means that overland flow might become more important at these sites, and would also disaggregate these soils. So, and again, this is something that you could address with this kind of convolutional model, because we could incorporate terms, say, for a changing grain size distribution through time, probabilistically, and you can incorporate terms for, you know, the percent of landscapes that are losing aggregates, however frequently, in a term for overland flow. We have not done that yet, but one thing that we are interested in doing is, at least from a kind of first order perspective, looking at just how far do we have to shift things in terms of non-local contributions, even just from considering this simple dry ravel case where some stuff starts to move farther. How often do we have to have that happen before the long-term erosion rates would be significantly affected given projected fire regime shifts? And again, we have not done this yet, but that is a tractable problem with the data that we're looking at.
Awesome. Thank you. No, that's great. That's great.
Okay, so if we don't have other questions, maybe we can stop now. Thank you so much, Danica again for this very interesting talk, and thank you also people that attend this week. Hope to see you all next week. So bye bye everyone.
Thanks a lot. It was great seeing you all.